So I've been working on this Voxel Rendering Engine, and the goal of this rendering engine is to have this beautiful light bouncing and bleeding effect without killing the frame rate of my laptop. My laptop doesn't have a GPU, so this is a bit of an interesting challenge. It is a virtual GPU with an Iris Intel graphics card, which I think is the equivalent of like a MX330, which is like a 7 or 8 year old graphics card. So I think I can make a beautiful rendering engine that runs perfectly on this. Currently, right now, this is working fine when the world is static. As you can see, the world's bouncing around, the light looks great, but as soon as I start moving, there's this stampede of logic and processing that happens when I'm generating new chunks. And it just causes my FPS to be absolutely abysmal. It's because I got a heap of moving pieces. The chunk generation is using cubic chunks. The light physics has to kick in immediately and be aware of everything that's happened before it to make this realistic global illumination. It's got realistic water physics where you place the water and it goes down the hill. It's got real-time shadows, which again, it also has to be aware of all of the previous processing that just went on. It's got water reflection where I can see the angle of the water and I can see this pixelated reflection of the world around it. And it's got this culling and optimization system that all has to kick into gear to make it run stably when you're just looking at something in the world and it's static. And it's really hard to know where to start to optimize something like this. I mean, obviously we have a heap of processing that goes on as soon as we generate the world. And it's hard to know if all of this processing is being done in the right way. I coded everything with a keep it simple strategy, right? Building the most simple version of my implementation possible. And I had a very clear idea for a cellular automata system that would basically let me approximate global illumination very efficiently. But I don't know if I've had mechanical sympathy for all the other pieces of the puzzle and the world generation, the noise sampling, all these other pieces that have to come together to make my global illumination system work smoothly. I'm going to be looking in this video for low-hanging fruit that can double my frame rate. And I'm going to be using a tool called Dev in a Box, which I'm working on, which is a tool that scans your code and basically finds all of the bugs and all the security flaws that exist within it. And I believe this can also be used as a tool to have mechanical sympathy, to understand how the software could do its work more efficiently or cost a lot less when it's doing the work. In this video, I'm just going to be looking for stuff that's easy to fix. I want to reduce the total work that's being done because my hypothesis is that I can just fix this by having a bit more mechanical sympathy, figuring out what works is being done that's redundant, or how I'm doing these calculations incorrectly for the CPU or GPU, fix that up and achieve a much higher frame rate. One of the main reasons for this approach, right, is that I don't know what the constraint is. I don't really know right now exactly what is slowing down my software the most. So I want this to be a smoke test for me to explore the system and to understand exactly what is really causing the biggest hang up here. So I'm going to break this into 3 sections, right, where I think the low-hanging fruit is most likely to be. The first is in the maths, right? Am I doing my mathematical calculations in the most efficient way? And one of the things I'm looking for here is some operations on the computer take less time than others. If I'm doing addition or basic logic checks, this is incredibly fast. But if I'm doing something like integer division or vector maths, it's much, much slower. And if these calculations are running millions and millions of times, as they are in a system like mine, a voxel game, that can be really, really bad. So if I can find any cases where I'm doing that incorrectly, that's an immediate speed up for my game engine. The second area is fairly obvious. I'm going to be looking at redundancy, right? Am I doing anything that I don't have to be doing? Is there anything silly that I'm doing? Have I made any mistakes that is just doing work that the computer doesn't need to do? And then the last area is going to be memory layout. And that's a little bit more complicated, but it's basically this idea that the way you arrange your memory has an effect on how the computer processes it. And if you have some more sympathy for how you lay out that memory, you can achieve a much better result. So let's jump into the math stacks. As you can see right now, when you load into my world, it's loading very laggy. There's a lot going on when it's happening, but you have these big spikes and big slowdowns, and it's very clear that all these operations that are going on have a bit of latency in them. And this is one of the reasons why I think there's a mathematical issue happening here, because you do have these big speed ups and slow down effects as the world is loading in. What I'm going to be doing is I'm going to be looking at my shaders in particular, and I'm going to be using my tool to scan a few different areas. So the main areas I want to scan are the fluid simulation, the global illumination system, and the chunk generation. And I'm just going to start now by just combing through for any mathematical shortcuts. And it's really popped out really quickly to me that there was 2 mathematical mistakes that I was making. And the first one was in the coordinate calculations. Essentially, I was using division in my coordinate calculations and also modulo calculus, where I could actually be using a bitwise operation. This was a good catch because the scanner picked up on the fact that the world was basically a power of 2 dimensions. It's 64, 32, that sort of thing. That's very, very standard for a Minecraft world. But because it was on these power 2 dimensions, I didn't actually need to be using division. I could just use bitwise operations. I could change these calculations very simply on a symbolic level, and it would be fundamentally simpler for the CPU and the GPU to process, which is great. The other optimization at Court, which I thought was clever as well, was I was using a vector maths library where I could actually hoist a lot of these calculations that I was doing out of this loop. And I didn't actually need to be using this vector 4 maths library. I could actually use raw scalar maths. Not only is this faster, it also eliminates a whole data packing and unpacking loop that I was doing, which is great. This is exactly what I was looking for. Everything's just running more efficiently just because I've changed essentially symbols in my code. Very, very simple stuff to do. But you can see now when I'm loading in, those initial frame rate spikes have actually dramatically reduced just by doing this. And this is just because we've replaced operations that were taking many, many clock cycles with stuff that is done in a single cycle. And streamlined a lot of the calculations, which is also going to have an effect on, as we go forward, making this engine a lot more responsive than it was before. Now, this bleeds straight into the redundancy tax, right? Now, I'm flying through the world. You can see that, we still have lag even after doing this. And I think that there is redundancy coming in here. Obviously, if I can find redundancy, this is the easiest way to optimize my system because it means I don't have to break anything. I don't have to change anything. I'm just eliminating something that's could already be eliminated. It exists for no reason. And the place to look for this is if there's something that's already calculated and I'm just recalculating it, or if a piece of information is static or unchanging, or there's some structure in the data that I can exploit, then I can eliminate redundancy. So I'm just going to be looking through these scans again. I'm looking at my ray marching system in particular, coordinates and how I'm calculating coordinates. Noise sampling is another spot where I'm kind of feeling that there probably is some redundancy. I have a bit more of a complicated noise system that I'm using, and I think that I've definitely probably made some mistakes there. I basically found 4 optimizations which I thought were really low-hanging fruit, and I was really curious to see the effect that they'd have on the world. The first was in my shadow rendering, right? So when I do this raycast of the shadow rendering, as it's flying through the chunks, it's got to look up specific information about those chunks, right? And I actually had not caught that the loop that was doing this would do it at every point in the ray march. So essentially constantly looking up, even though the chunk hasn't changed. And there's a really simple way to refactor this so that I basically only look up the chunk's data and I cache it when I go over a chunk boundary. Super simple optimization, reduces the amount of work in the shadow calculations by quite a bit. I had a loop in my code where I was doing a complex coordinate calculation of basically trying to figure out, which the next block in the chunk that I'm going to, and I had to look up a bunch of metadata and stuff about it. It's basically like a rung length encoding packing algorithm that I was doing. And what the system identified was that actually the data structure that I was operating on in this loop was already sequential from something else that I'd done earlier. And so I don't actually need to do this calculation lookup. I can just do a +1 and I will automatically be at the next coordinate that I would have looked at anyway. Super simple. You'd think, hey, why didn't you catch that when you're building the system, right? Well, this is a massive piece of software. And obviously, when you're trying to build something the first time around, you're just trying to get the ideas out on paper and then make it simple. I do believe that is a pretty good principle of software development, is that you should put the simplest thing down first and then come in later to do this sort of optimization work, and this sort of stuff does slip through. The fact that the engine was able, the scanner was able to identify that this was a sequential piece of data was tremendous, because I didn't catch this when I was writing the code. It's a really good point of having mechanical sympathy for the software and understanding that the software has already done some work and we don't have to do it redundantly. There was something similar to this as well in how I was doing the noise generation. So when you're generating like a voxel world, you basically have to sample noise, and that's how you get like the shape of the hills and all this sort of stuff. And make the world interesting. And in my system, I have chunks, and then inside chunks, I have volumes. And volumes serve a purpose for the cellular automata calculation to basically optimize that and speed that up. But those volumes need to know about the noise calculation. And specifically, they would recalculate and sample the noise at each of the borders between the volumes, right? What I hadn't caught is, of course, you could actually just sample the noise for the chunk and then cache that, and then that already implicitly had all of the noise data for the volumes, while I was in my code currently still sampling the noise at all of these borders. Another really simple, having understanding about the code base and pulling it up and having a bit more sympathy. It may have been simpler to write it the way that I did, but this was actually the more efficient and the more logical way to do it overall. Another really obvious redundancy, right? And I think redundancy is a point where, you are going to feel a little bit silly when you see it because stuff just pops out that you didn't expect. In my shaders, I had a bunch of constructions that were happening, and these constructions were the same across all of the different shaders, but also could be constructed on the CPU once, uploaded to the GPU, and then some slight modification could be done to it. But 90% of the work could be done once. And I was constantly recalculating this. So this was another optimization where I basically pulled this stuff out, put it in constant memory, and then used it once and shared it across all of the threads. Every single one of these reduced redundant computation and data setup, and none of these changed the way my algorithm worked. As we fly through the world now, you can see it's smooth and seamless, and there's no major lag or anything like that happening anymore. And all of this is just because we freed out a massive amount of work that the CPU and GPU was doing that it just didn't need to do. I haven't changed how the code works at all. This is the same code as before, just with some slight refactoring to remove work that didn't need to be done. Now, the last area is the memory layout tax idea, which is basically this idea that you can structure the way you're pulling in objects into memory so that they have a bit more sympathy with the machine. And at this point in the video, I was starting to realize that I did have a constraint in my software. I found this because as I was going through the process, I noticed a ton of optimizations around my water, and my water being a significant bottleneck. And I actually tested this in my game, and I could see that when I had my water in my world, it was dramatically slower than when I didn't have my water in my world. Now, in my game, water has a lot of moving elements. It literally is a moving element. But most of the time, when you fly through the world, all of these lakes and rivers are static. And I started to ask myself, is there a smarter way to do this? And I suspected that memory layout would be a way to do it. So I basically did a bunch of scans on the water domain and the water simulation. And I identified this idea, essentially, that the way we were using the memory around the water was very poorly done. Basically, when we were pulling the water object in to do processing to figure out the height and level of the water and if it needed to flow and all this sort of stuff, we were pulling in a bunch of metadata that we didn't actually need alongside the data that we did need to do the calculation. And essentially, the first optimization that I found in the system was this idea of turning it from an array of structures to a structure of arrays. And what that means is basically you're separating the data out into two different groups. You have the array of data that is used for one process, and then an array of data that's used for another process. Really simple idea. But what this allows you to do is essentially when the computer goes to look up the information, do the work, it's going and looking at a cache first. And it has a series of caches before it gets to the main memory. And then if it goes to main memory, it takes longer to find stuff, but it'll eventually find your thing. But the idea is if you can structure the data better, it can fit in the cache much more efficiently, which means it doesn't have to look through this deeper nesting to find your data. So that's essentially how that works. Now, one of the cool things about this optimization was it immediately allowed me to do another optimization called single instruction multiple data, which is called SIMD as the acronym, but really it's just a really smart way to do parallelization. That's basically the computer chip can parallelize the equation using matrix maths and all that sort of stuff. But basically, because I'd restructured this data to be very focused on one thing, I could use matrix multiplication and smart algorithm design to basically, instead of doing one calculation at once, I could do 16. Now, this had a really dramatic effect. It made the water blazingly fast and no longer had any effect on the FPS, just because all of these calculations, all of this redundant data wasn't being transferred, and I could parallelize the actual calculations that needed to be done. So it removed a bottleneck almost immediately. And now we can fly through the world with the water through it, and everything is running much faster. And we've basically achieved our goal of doubling the frame rate. And the game now is super fast. It's playable. I could build a game on top of this. I've got some more work I want to do. I want to show off some bug fixing in it as well. But this works. And the truth of the matter is this is all really simple stuff. There is more complicated optimizations that were suggested by the system. Stuff that would require me to rip things apart and change how things work. But it's crazy that I could just double my frame rate just with some very simple optimizations that literally took about 2 to 3 minutes to find. And each one of them only took about 4 to 5 minutes to implement, especially the one where it's just changing the symbol. I really got a kick out of that one. So this has been a really good test of my software. We don't have optimizations in Dev in a Box yet. It's only bugs and security flaws, but I think this really shows that our system does understand code and can have sympathy, mechanical sympathy for how the CPU and the GPU work to figure out all the different ways that you can save money and speed up your software. And I'm really excited about that. I'm looking forward to showing off some more around that. So thanks for watching.